Hello and welcome back. In this video, we're going to be taking a look at concepts involving circuits. Let's begin. Please feel free to pause and rewind the video as necessary. What conceptually is electric current? Well, electric current can be viewed and defined as the flow rate of charge through a conducting wire. And so electric current is the flowing of charged particles through a wire between 2 points that have different electrical potentials. We'll be focusing mainly on DC electricity, but it's helpful to contrast that with AC electricity too. DC stands for direct current and AC stands for alternating current. Direct current is when the charged particles move in only one direction, meaning they move in a single loop from one side of the battery, the positive side, to the negative side of the battery. This is found in circuits that contain batteries. Alternating current is when the charged particles move back and forth, in other words, in both directions along the same wire. This is the type of electricity that is coming from the power companies to power our homes and businesses. Explain the difference between conventional current and electron current. Well, not much was known about the existence of electrons during the time when experimentation on electrical current was happening. Therefore, it was always assumed that current was the flowing of some sort of positive charge. Electron current is defined as the electrons traveling from the negative terminal and attracted to the positive terminal of the battery. Conventional current, which is what we will use to study electric circuits, is defined as the direction in which positive charges would be flowing, if positive charges indeed would flow. It's a convention that has stood for over 200 years, and we still use it. Give the basic equation for electric current. Electric current is I is equal to Q over T. Where I is the current in amps. A stands for amps or amperes. Q is charge, again in coulombs, and T is time in seconds. So we can think about electric current as how much charge is passing a certain point in a certain amount of time, or the flow rate of charge. Section 16.2, battery and EMF. Explain what electromotive force is. Well, it's not actually a force. Rather, EMF represents the amount of work done by the battery per unit charge to move charges from the one terminal, the positive terminal, to the other terminal, the negative terminal. Let's take a look at an analogy for electric circuits. A pizza delivery person must go from the pizza shop to a customer's house, then back to the pizza shop. Is it possible for the delivery person to take the same path going to and from the customer's house? Well, yes, it is. The pizza shop, the delivery driver could gather the pizzas, and take them to the customer's house, deliver the pizzas, and then return back to the pizza shop to gain more pizzas. In this analogy, the pizza car is like the charges in an electric circuit. The roads are, of course, the wires. The pizzas represent the energy that is carried by the circuit. The energy is gained by each charge from the EMF of the battery, and those pizzas are delivered or given off to the customers. The customer's house represent a resistor. They represent resistors in the electrical circuit. Just as the customers receive pizza from the deliverers, resistors receive energy from the batteries. And a lower amount of pizza exists in each charge every time a pizza is delivered to a customer's house. Therefore, just like the electric potential would be less as current travels across a resistor. And the pizza shop is much like the battery. Within the battery is the EMF, which is supplying, again, the work done to move charges from the positive end to the negative end of the battery. But it's like telling how much energy each pizza, right, each charge is going to receive. So each deliverer, which is the charge, is going to receive a certain amount of energy. And the EMF is much like what is telling each delivery driver how much pizza they're going to carry, or how much energy each charge is going to deliver. Again, this is like the pizza shop telling the delivery driver how many pizzas to carry. Translate each diagram into a circuit diagram, then state which of the circuits light the bulb and why. It might be helpful to do the chart on the next page before doing this question. Well, in this chart, the symbol that represents a straight line would be a wire. And wires simply transport charges around the circuit. They are conductors. The symbol with uneven parallel lines is a battery. It's helpful to know that the long end of the battery is the positive end, the short end is the negative end. When you have multiple uneven parallel lines, that's usually an indicator of a higher voltage. Usually, batteries are drawn with just one pair of uneven parallel lines. Batteries, again, provide the energy given to each charge moving through the circuit. The zigzag lines in the middle of the straight line represent a resistor. And resistors are devices that convert electrical energy into some other type of energy. They usually heat up, so usually that other type of energy is thermal energy. It could be light energy as well. It varies on the resistor. An example of a resistor would be a light bulb. And so a circle drawn over small L shapes are an example of how you draw the symbol for a light bulb. And light bulbs are resistors that convert electrical energy into light and thermal energy. The symbol that looks like an open bridge is a switch. And switches are devices in the circuit that help control the amount of current in the circuit. They can turn on and off the current in a circuit. The symbol with the A is called an ammeter, and it is placed in series within a circuit to help measure the electric current in that circuit. The symbol with the letter V is a voltmeter. And voltmeters are devices that are hooked in parallel across some device to measure the electric potential difference at 2 points across that device, or at any 2 points in a circuit. And the symbol with 2 even parallel lines is a capacitor, which are devices that store electric charge in the circuit. Section 16.4, Ohm's Law. Explain what resistance is. Resistance is the quantity that describes how a circuit element resists current in a circuit. The symbol is R, and the unit is the ohm, which can be written out as OHM, or it can be drawn as the uppercase Greek letter omega. Ohm's law is a relationship that predicts the value of an electric current through a resistive device when the potential difference and resistance are known. For an object to be ohmic, it means that the resistance does not depend on the potential difference across it. A non-ohmic device does, and it's one that cannot be modeled ohmically. Other such symbols that you can see are also variable voltage sources, and you could even see an arrow drawn through a resistor like this to be a variable or changing resistor too. We will do the design and experiment part in class together. But let's take a look at some data in terms of how an ohmic resistor might look like and a non-ohmic resistor might look like. Let's take a look. Here, let's go ahead and build a circuit. I'm going to attach a resistor here. And if I tap on the resistor, I can see its value is 10 ohms, which is fine. I'll leave it at that. In series with this circuit, I'm going to attach an ammeter so I can measure the amount of electrical current passing through this circuit. Now, if I close it, you can see how much electric current is passing through, but I want the battery to be variable, so I'm going to adjust the battery to varying amounts. And I'm also going to hook up a voltmeter to the resistor, the negative end of the battery, the black end, the black probe goes to that. And the positive end of the battery, well, the red probe goes to the positive end. A lot like jumper cables. Red to positive, black to negative. And that allows me, and if you ever hook it up backwards, you'll just get a negative symbol on your voltmeter reminding you, oops, I hooked it up backwards. Closing this, we get about 0.2 amps of current. If I increase the voltage to 4, you can see the current has gone up to 4.4 amps. 6 volts. You can see the current has gone up to 0.6 amps. 8 volts, the current has gone up to 0.8. And 10 volts, the current has gone up to 1 amp. Modeling this data right here. And if we were to graph this, this would look like a straight line. In other words, it would be very predictable. Now, using our Ohm's law relationship, Ohm's law predicts that the potential difference is equal to the product of current times resistance. Now, current was the dependent variable, voltage was the independent variable, and if I write them as such, divide this both sides, and then move the R over here, this rewrites to current over potential difference equals 1 over R. Well, the current would be our rise, the potential difference would be our run, and 1 over, or the inverse of the resistance, would be your slope, which means your resistance would be the inverse of your slope. Since your slope is constant, your resistance will be constant, and thus this is considered an ohmic device. Let's see what happens when we hook up a non-ohmic device. Now, attached to this is an ordinary light bulb. And you can see, instead of the 0.2 amps that was going through the resistor at 2 volts, only 0.15 amps. And as we increase the voltage, even as high as 10 volts, we can see that we get a maximum of 0.54 amps. Modeling this data. At 2 volts, 0.15 amps of current passes through the light bulb. At 4 volts, 0.27 amps. At 6 volts, 0.37 amps. At 8 volts, 0.46 amps. And at 10 volts, 0.54 amps. Yielding a non-constant curve. This is an example of a non-ohmic device because the slope is not constant. What does it mean for elements to be in series? What do all elements have to have the same to be in series? Well, all elements are in series if they are arranged on the same path of current. If they are in series, they have the same charge and the same current. To be in parallel, circuit elements have to be arranged on separate paths of current. The potential difference is the same in parallel. We will be going over this in class. Section 16.6, Joule's law. Explain what power is, give the units and symbols, and the 3 basic equations for electric power. There are actually 4 equations. We'll go over all 4. Electric power is the rate at which electrical energy is converted into thermal energy. Power is equal to energy divided by time. It is the rate of energy transformed or delivered to a particular device and transformed into thermal energy. But there are 3 electrical power formulas that we can use as well. And we will derive all 3 of these in class. P equals IV, power equals current times voltage. Power equals current squared times resistance. And power equals voltage squared divided by resistance. We will go over how we derive each of these in class. A kilowatt hour is a unit of electrical resistance used by electric companies to charge customers according to how much electrical energy is used. We will go over this example in class together. We will also go over this example in class together. Move along to page 9 of your notes. Section 16.7, Kirchhoff's law. Kirchhoff's loop rule states that the sum total of the charges, that should be charges, that's a typo, not changes, adds up to 0. The sum total of the electric potential around any closed loop is 0. The junction rule states that any current going into a junction needs to add up to the same amount of current going out of a junction. And we will apply both of these rules in our circuit analysis. Equivalent resistance is like replacing several resistors in a circuit with one that has an equivalent resistance that could pass an equivalent amount of current through it. We will do these examples in class together. What does resistivity depend on? Well, resistivity is used, but the symbol is rho, the Greek letter rho. And the units are the ohm meter. Resistivity depends on the resistive material in terms of what it's made of. It depends on the number of free electrons per atom in the material, as well as the degree of difficulty the electrons have moving through the material due to their interactions with the material. Superconductivity is characterized by taking the resistance essentially down to zero, and thus the resistivity down to zero. This was originally done by taking a sample of mercury and submerging that sample in a very cold environment so as to decrease the temperature to 4.2 Kelvin. Upon doing this, it was discovered that the resistance dropped to zero, and thus the resistivity had to drop to zero, leading to superconductance. In the last 20 years, little typo there, superconductivity has been experimented with and has been found to occur at much higher temperatures, such as 135 Kelvin. The following examples on resistors and capacitors together in a circuit will be done together in class. Again, pause the video as necessary and rewind as necessary. Thank you.